Electric cars have a weight problem. Electric aircraft have a weight crisis. On the road, more batteries reduce efficiency. In the air, every extra kilogram must be lifted for the entire flight. Add too much battery, and the aircraft loses the passengers or cargo it was built to carry. That is why electric trainers already fly, while regional electric airliners mostly do not. Solid-state batteries could change that. By replacing flammable liquid electrolytes and enabling lighter lithium-metal designs, they promise far more energy for the same mass. The target everyone talks about is 500 watt-hours per kilogram. But is that really the number that makes commercial electric aviation possible? Jet fuel stores far more raw energy than batteries. Electric motors narrow the gap because they waste much less energy, but the battery still remains on board after it is depleted. This is where impressive announcements become confusing. A laboratory material is not a cell is not a battery pack, and a battery pack is not a certified aircraft. An aviation pack needs protection, monitoring, temperature control, and reserve energy. Every layer adds weight. So the useful number is not the best cell result in a laboratory. It is the energy available from the complete aircraft pack, delivered safely at takeoff power through heat, cold, vibration, and years of service. In a conventional lithium-ion cell, lithium ions move through a liquid electrolyte. It conducts ions well, but its organic solvents can burn. A solid-state battery replaces most or all of that liquid with a solid material. Depending on the design, that may be a ceramic, sulfide, polymer, or a hybrid. The change can also enable a lithium metal anode, storing more charge for less mass than graphite. In theory, that means more energy inside the cell and less weight devoted to controlling flammable liquid. But solid materials bring different problems. They must stay in close contact while the battery expands, contracts, vibrates, and ages. Ceramics can crack. Interfaces add resistance, and some designs need constant pressure. The chemistry may be solid. The engineering challenge is not. Solid-state batteries are often presented as fireproof. That goes too far. Research has shown lithium filaments crossing hard electrolytes through microscopic cracks and imperfect interfaces. A solid separator can reduce risk, but it cannot make every failure mechanism disappear. For aviation, the real test is simple. Can the aircraft detect a failing cell, isolate it, and stop the heat from spreading? In late 2025, Swiss company H55 completed authority-witnessed module tests that contained thermal runaway without propagation using commercially available lithium cells. That result matters because it shows that good monitoring and pack architecture already improve safety. Solid-state chemistry may help even more, but it will not remove the need for careful engineering. So, how close are we to 500 watt-hours per kilogram? NASA's experimental SABRES program has exceeded 500 in small research prototypes. That is genuine progress, but it is not an aircraft pack. QuantumScape publishes about 301 watt-hours per kilogram for its packaged solid-state cell. Factorial has reported 375 for development cells. Meanwhile, Amprius advertises lithium-ion cells reaching 450, showing that solid-state is not the only path forward. These numbers describe different products at different stages, so a simple ranking is misleading. The winning battery must combine energy with takeoff power, useful cycle life, safe fast charging, reliable manufacturing, and a price airlines can afford. 500 is an important target. It is not a finish line. While battery companies improve the chemistry, the rest of the aircraft is already moving. Pipistrel's Velis Electro became the first type-certified electric aircraft in 2020. Its short endurance shows today's limits, but it proves certified battery flight is possible. Beta Technologies is flight testing larger aircraft for cargo and special missions. Safran has certified an electric aircraft motor, while several aerospace companies are testing megawatt-class hybrid systems. Together, these programs reveal the likely sequence: trainers first, then cargo and special missions, hybrid regional aircraft next, and larger all-electric passenger aircraft only when the complete system is ready. The timeline becomes clearer when we look at actual aircraft projects. Heart Aerospace is developing the 30-seat ES-30, with type certification targeted for 2031. Elysian is studying a much larger battery electric aircraft for the early 2030s. Those are serious programs, but they are targets, not airline fleets operating today. Before passengers board, manufacturers must prove the cells, pack, motors, software, charging system, and everyday reliability of the aircraft. Regulators then need evidence that the complete system is safe. Airlines do not buy watt-hours per kilogram. They buy an aircraft that can complete its timetable every day at a predictable cost. If those pieces come together, regional travel could change in very practical ways. Electric motors are efficient, quiet, and mechanically simpler. The best early routes may connect communities separated by water, mountains, or long road journeys, rather than replacing efficient electrified rail. Hybrid aircraft can begin the transition sooner, using batteries for the most demanding parts of flight while keeping fuel for range and reserves. As batteries improve, the electric portion can grow. The change will appear route by route: a trainer, a medical or cargo flight, a hybrid commuter, and eventually a battery electric regional aircraft carrying paying passengers. It will look more like a staircase than a sudden revolution. So, will solid-state batteries finally make commercial electric aviation real? They could become one of its most important enablers. Higher energy and lower flammability would give aircraft designers options they do not have today. But solid-state is not a magic shield, and 500 watt-hours per kilogram is not a boarding pass. The real breakthrough will be a complete pack that delivers energy, power, durability, manufacturability, and certifiable safety at the same time. The clues are already here: a certified electric trainer, safer pack designs, certified motors, flight demonstrators, and solid-state cells moving beyond the laboratory. Commercial regional fleets are not here yet, but the engineering path is finally in plain sight. So there you have it. That's what it turns out to be. If this answered a question you didn't know you had, hit subscribe so you don't miss the next one. And if you liked it, tap that like button. Turns out, it actually helps a lot.